now be talking about Lab 5, Projectile Motion ++. So, what's the purpose of this lab? The purpose of this lab is to observe how an object energy changes as it is thrown into the air and follows the projectile trajectory. Additionally, we will also observe the differences between the results with and without drag. But first, let's talk about some physics principles. The first principle is Newton's second law, which says that the rate of change in momentum is equal to the vectorial sum of forces on a body. And we've done this for all 4 labs. The second formula is the velocity update formula, and this has also been used in lab 1, lab 2, and all of the labs. Again, here's gravity, just Fg equals g mass 1 mass 2 over r squared times the direction of the position. And on Earth, the gravitational constant is 9.8. The next force acting on our object is drag, which is just Fd times negative because it's going opposite direction of the velocity, negative b velocity squared times v hat. And finally, all of the energy formulas. So kinetic energy, gravitational potential energy, and spring potential energy, which are just formulas that you can get from the formula sheet. So what are the steps of this experiment? First, we'll create a computational model of a paper ball without drag in GlowScript. Second, we'll create a computational model of the paper ball with drag in GlowScript. And finally, we compare the results with and without drag. The conditions and setup are just a crumpled ball for the object, and the initial conditions are the same as a recorded video we used for reference, with the same starting mass and same starting velocity. Now, let's look at the GlowScript. The first part is just setting up the initial values of the ball's mass and velocity. So we have here ball's mass, the positions, and the velocity. Then, in the bottom section, after calculate net force, is the part of the code within the iterative step. So first, we calculate the net force, which for the case without drag is just gravity. And then we apply the velocity and position update formula to update the velocity and position. Next, we calculate the net force with velocity, and then again update the velocity and position. Finally, we calculate the kinetic and gravitational energy for with and without drag. And let's see what it looks like. So let's look at the results. In both cases, the kinetic energy is a upward facing parabola, and the gravitational energy is a downward facing parabola, which matches what we expect. Now the thing to note here is that the energy with drag slopes down a lot more than the energy without drag. And this is to be expected since drag is doing work in opposite direction of wherever we're moving. So it's decreasing the total energy of our system. But something to notice is that even when there's no drag, we're still experiencing a drop in energy. Why could this be? So what are some possible errors? One is that the time steps might be too large, causing our simulation to be inaccurate. Another thing is that the method of updating velocity and position may be accurate, and a method based on integration may be better for this case. What if the object was thrown in real life? Will the loss of energy match the simulation with drag? And I would say no. Since there are many types of energies involved in a real system, there would also be a lot more ways that energy could be lost to their surroundings, causing an even greater drop in total energy. And what do the results mean? How much does drag affect the energy loss of a system? Drag creates a significant work in the negative direction on an object's momentum, as we've seen in the change in energy. And yeah, it can be shown that energy drop with drag is much greater than without, and also we can see that the object moves less with drag.